Hi grade 12s, and welcome to my channel. To the new subscribers, thank you so much for subscribing and welcome. And also to the old subscribers, welcome also. I know I haven't posted anything in a while. I haven't posted any video for the past 2 weeks, and that is because I have been having bad flu. But at this moment, I'm back with another bang, and we are continuing from where we left off. So if you did watch the previous videos, you would have seen that we had started with calculus. We have covered the past two, the first two parts of calculus, and this is part 3 where we are doing the cubic graph. What do we mean when we say a cubic graph? So a cubic graph is just any graph that has two turning points, meaning it can either be a local maximum, a local minimum, or it can start with a local minimum and a local maximum. So that is your cubic graph. And just like any other functions, we have a standard equation for a cubic graph: ax cubed plus bx squared plus cx plus d. So that is the standard equation for a cubic graph. And from this equation, if you are being given the equation of a cubic graph with values, this part would represent your y-intercept, and this part tells you the shape of the graph. So the shape, meaning if your a is greater than 0, if your a is positive, you are starting with a local maximum, then a local minimum. If your a is negative, you are starting with a local minimum and a local maximum. So that is how a tells us the shape of your cubic graph. And I'm going to highlight a few things that you need to sketch a graph. So the first thing that we're going to focus on is sketching a cubic graph. And sketching a cubic graph, you need there's a few coordinates that you need to work out. The first one is your shape. Okay, your a is gonna tell you the shape of the graph, so that would be from the value of a. And then secondly, you need to work out the y-intercept, which in most cases, if they have given you the full equation, it means you will just take that value, and we know at the y-intercept x is 0, so your coordinate for y-intercept would be 0 and d, meaning that d over there, so it would be a value. And then the third thing is your x-intercept, and your x-intercept, we know at the x-intercept y is 0. So in order for you to get your x-intercept, you need to factorize a cubic equation. Factorize a cubic equation, which we are going to cover up as we sketch a graph. So you need to factorize a cubic equation. And then now the fourth thing is your turning point. I'm going to introduce some terms that they like to use under the cubic graph or the calculus, which also means turning point. So turning point is the same thing as your local maximum or your local minimum. Or if they say calculate stationary points, your stationary points means also the turning point. Stationary points, these are also a turning point. So that and that and that, it's the same thing. So you don't have to worry. If they say calculate stationary points, you're going to do the turning point. If they say calculate local minimum and local maximum, you're going to do the turning point. And the fifth thing that we have, or that we have to find, is what we call the point of inflection. The point of inflection. So with the point of inflection, I'm going to cover up what this is when we go down and sketch the graph. Okay, so these are the 5 points that you need in order for you to sketch a cubic graph. Okay, so let us have a look at an example where we have to sketch the graph of f at x is equals to x cubed minus 5x squared plus 8x minus 4. So remember, we had said the first thing is our shape, and already we can see our a, the number in front of x, is a positive one, so it means a is greater than 0. We are working with a local maximum first and then a local minimum. And then the second thing is our y-intercept, and we said our y-intercept comes from the value of d, and for our y-intercept x is 0, and then your y-intercept would be the -4. So it's 0 and -4. The third thing, before going to x-intercept, let us look at the turning points, or the local minimum and local maximum. So for turning point, what you should know about calculating the turning point of a cubic graph is that you need to first find the first derivative, you equate it to 0, then you solve for x. Then you take that x value, you substitute it on the original f at x equation that they have given you, meaning we will substitute it there. So let us now derive f at x. So the first derivative, we have 3 times 1, that would be 3x to the power of 2 minus 5 times 2, that is -10x, and then 8x, we just have 1 times 8, which is just 8. So this is our first derivative. Then we are going to say 3x squared minus 10x plus 8 is equals to 0. And we're solving for x. Since x has a coefficient of 3, we can use the quadratic equation. X is equals to minus 10 plus or minus square root of minus 10 squared minus 4. Our a is 3 and our c is positive 8, all divided by 2 times a, our a being 3. So plugging this on my calculator, x is 2, or x is 4/3, 4 over 3. And then remember, we had said you are taking the x value and substituting it on the original equation, meaning to find f2, okay, fx is x to the power of 3 minus 5x squared plus 8x, and then the constant was -4. So it's x cubed minus 5x squared plus 8x minus 4. So to find the y value there, I will say f at 2 is 2 cubed minus 5 2 squared plus 8 2 minus 4. And plugging that on my calculator, it gives me 0. And then doing f at 4 over 3, that is 4 over 3 cubed minus 4 over 3 squared plus 8, 4 over 3 minus 4, and that gives me 4 over 27. So it means my turning points, I have 2 and 0. I also have 4 over 3 with 4 over 27. Okay, so now we have the turning points, and then now let us go to our x-intercepts. So I had stated earlier that to find the x-intercepts, you need to factorize a cubic equation. So we know the x-intercept would be the path of the graph that intersect with the x-axis, and we know that when it intersects with the x-axis, y is going to be 0, meaning we're taking our f at x, we equate it to 0, meaning we have x cubed minus 5x squared plus 8x minus 4 is equals to 0, which is our original equation. And the next thing we have to factorize. So now I'm going to teach you how to factorize a cubic function or a cubic equation. The first thing that you need to find the first vector. So for you to find the first vector, it means you want to substitute values, a single value on x, that when you substitute it, it gives you 0. So the range of values that you can choose from 1, 2, 3, -1, -2, -3. So I'm just gonna start with my 1. Substituting 1, the answer that I get is 0. So if I substitute, so f at 1 is equals to 0, meaning 1 is a factor. How do I write it now? Remember, it means x is equals to 1 is a factor, but because we want to factorize into 3 brackets, when you now put it in a bracket, if it was positive, it becomes a -1, and then you have the one big bracket. So what I'm quickly going to do, I'm going to write that equation again. So we have x cubed minus, okay, that's supposed to be a cube, minus 5x squared plus 8x minus 4 is equals to 0. We have found our first factor. We said it's x minus 1 because when we substituted a positive 1, it gave us a 0. And now the main thing is for us to find the big bracket. So in the big bracket, we first want to find a quadratic equation, then we will factorize the quadratic equation into 2 more brackets. So I want you to now follow the steps. So the first thing that we do, we're going to start with the first factor. So the first thing that we ask ourselves, so we are going to start with x cubed, and we say, what can I multiply? Okay, I just want to circle the x cubed there. What can I multiply this x with so that I can get x cubed? So we know that x times x squared is x cubed, meaning this is going to be x squared, because when you say x times x squared, it's going to take you to x cubed. That is the first thing that we do. And then the next thing, we are going to look at the last term. So the last term is your -4. So now with your -4, you are working with the -1. You say, what can I multiply -1 with to get -4? So -1 times +4 is going to give you -4. So -1 times 4 is -4. So it means there you're going to put a +4. So you got your first and your last term for the quadratic. And now the most important part is for you to get the middle part. So to get the middle part, you're going to use the second term of your cubic graph or your cubic equation. And when I say the second term, I mean the one that has an exponent 2, the x that has an exponent 2. And then in doing so, we know that term, it's -5x squared. So you're going to focus on -1 and x. -1 times x is -x squared. And then you are saying, what can I add or subtract to -x squared to get -5x squared? -x squared, -4x is gonna give us that. So it means that is gonna be -4x squared. So -x squared, -4x squared is -5x squared. And then now one last thing, with the -4x squared, you now take it to the first term. I'm still gonna use green because it's still part of that term. We say that x there times something must give us -4x squared. So that would be x times -4x. That -4x is your middle term there. I hope this makes sense. If you feel like you need to see me doing more examples on factorizing your cubic equation, feel free to let me know in the comment section so that I can just make a short video doing different types of cubic equation, factorizing them and solving for x. So it means now our factors, we have the x minus 1 that we got earlier, and then we are going to factorize x squared minus 4x plus 4, and that is going to give us 2 brackets because that's a quadratic. I'm just going to bring in my 2 brackets. So I have x, then I have -2 and a +2, because -2 times +2, no, it shouldn't be. So it's -2 and -2, sorry. So -2 times -2, it's +4. -2 is 4. So it means x is 1 or x is 2. So our x-intercept, remember we had said y is 0, so you have 1 and 0. You also have 2 and 0. So that is what we have on sketching the graph. We have your shape, you have the turning points, we have the x-intercept, we also have the y-intercept. I know that I did mention earlier that we also need the point of inflection, but because with the point of inflection there's a lot of theory that I want to highlight under it, I'm just going to sketch the graph without the point of inflection, like working it out. Then as we move along with the lesson, we are going to cover up the point of inflection and get the story about it. So the shape of the graph, we have stated that it starts with a local maximum and a local, followed by a local minimum. And then I'm just gonna put in my points. So starting with the y-intercept, where y-intercept was -4 and 0, which I'm gonna put there. And then for our x-intercept, we have 1 and 0 and 2 and 0, meaning I'm just gonna stretch this one a little bit to that side. Then I have a 1 there and I have a 2 there. That would be our x-intercept. And then we look at the turning points. Our turning points, we had 2 and 0, meaning the x-intercept there, it's also a turning point. Then we also had 4/3 and 4/27. So 4/3 is equivalent to 1,33. I'm just gonna write it as a decimal so that I can be able to bring the accuracy. 4/27 is equivalent to 0,15. So that would mean that I'm plotting in between there, and then it will go all the way there. So it means, because the graph starts with a local maximum followed by a local minimum. Let me just start with the turning point there, the first turning point and the second turning point. Remember, at 2 it's a turning point, so the graph must turn, and then we also go all the way to 4, and then there we have the graph. But I think it can look better than that, so I'm just gonna try and make this look like a turning point. So yeah, something like this. This is the graph. Then you're just gonna show the coordinates for your turning points, and then also the -4, the 1 and the 2. Then we are done. We have sketched the graph. Okay, so now that we have seen how we can sketch the graph, I had mentioned earlier that we will come back to the point of inflection. And when we describe a point of inflection, we say this is the point where the graph changes concavity. So a cubic graph changes concavity. So we have seen also that when you are looking at a cubic graph, it has 2 stationary points or 2 turning points. So if we are looking at a graph that, let's say, starts with a local minimum and followed by a local maximum, we will say the first part is concaved up, and the second part, this part is concave down. And then a point where the graph will change from being concaved up to a concave down, that would be somewhere there, would be now called our point of inflection. So the first thing that we also, okay, not the first thing. So the point of inflection, it is halfway between the turning points. It's halfway, or is the midpoint. Let me write it as like this. It's the midpoint of the turning points, of the 2 turning points. It's the midpoint of the 2 turning points. Meaning, in the first method in which you can calculate the coordinates of the point of inflection is to use midpoint formula. If they do provide you with the 2 turning points, and let's say that is -2 and 3, and not 3, let's say it's -2 and -3, and then there we have 1 and, let's say, 1 and 2. So to find the x coordinate there, x would be -2 plus 1 divided by 2, which is going to be -1 divided by 2, and that is, yes, -1/2. That is the x coordinate of your turning, of your point of inflection. And in order for you to find the y coordinate, you are going to substitute that x on the original equation of your f at x. So that is the first method that you're going to calculate the x coordinate of your point of inflection.
Then the next thing that I'm going to mention with the point of inflection is that we relate or we link the point of inflection with what we call second derivative. So with second derivative, it means you have your cubic graph equation, you derive it, and then after deriving it, you get the first derivative. And then when you take the first derivative, remember this one, we link it to the turning point. When you take it and you now derive it for the second time, you have the second derivative. Meaning this one is for the turning points and this one is for your point of inflection. So with the second derivative, you are now working with your point of inflection. And then now bringing the second derivative. So the second derivative, we say it is positive or it's greater than 0 when the graph is concaved up. And it is negative, meaning it is less than 0 when the graph is concave down. So this would help when we answer those theory questions which can be phrased in this way: for which values of x, for which values of x, value or values of x is, and then number 1, f at x greater than 0, number 2, f at x less than 0. So I'm just gonna draw just a normal graph, a normal cubic graph, and let's say at the point of inflection, we have been given the point of inflection to be like the -1/2 that we got there, and then the y is -1. So for which, okay, I need to come back there, that is supposed to be second derivative. For which values of x is f at x greater than 0, we mean for which values of x is the graph concave up. You're just going straight to the graph. You don't have to solve that mathematically. You go to the graph, you're going to use the graph and you check, yes, the graph is concave down there and it is concave up that side. So for which values of x is f at f double prime x greater than 0 means where is the graph concaved up. We can see the graph is concaved up. Remember here concavity changes, meaning any x values before the point of inflection, before the x value of the point of inflection, the graph is concaved up. Any x values after the point of inflection, the graph is concave down. So remember that means concave down. So when you write this now, always if you are answering questions on concavity, you're going to use the x value of your point of inflection and would say when x, for question 1, the answer would be when x is less than -1/2. For question 2, the answer would be when x is greater than -1/2. So we are saying from when x is there, from there going all the way to the left of the of that point of inflection, the graph is concaved up, and then going to the right of the point of inflection, the graph is concave down. So every time when they ask questions about concavity, the answer has to be either less than or greater than the point of inflection, the x coordinate of the point of inflection. So that is the theory that we need to know about the point of inflection. And then being given the graph or being given the equation of a graph, let's say f at x is x cubed minus 5x squared plus 8x minus 4. We are being given this equation and they ask us to calculate the coordinates of the point of inflection. Calculate the coordinates of the point of inflection. So the first thing that we do, we will first derive the original graph. That will be 3x squared minus 10x plus 8. And then remember we said point of inflection, we work with second derivative. I'm going to derive now that into that. So that's going to be 6x minus 10. And then once we have derived that, we say at the point of inflection, f at x is equals to 0. So we have 0 is equals to 6x minus 10. So 10 would be 6x. Therefore, x is going to be 10 over 6, which is 5 over 3. So now we have calculated the x value. To find the y value, we do f of 5 over 3, and that would be 5 over 3 cubed, 5 over 3 cubed minus 5 over 3 squared plus 8 5 over 3 minus 4, and that's going to give us 5 over 3 cubed so that gives me a y value of 2 over 27. So it means the point of inflection, the coordinates are 5/3 and 2/27, and we are there. We have it.
Okay, grade 12s. So now that you have settled into our cubic graphs, you know how to sketch a cubic graph, you know how to, most importantly, find your turning point, find your x-intercepts by factorizing a cubic function or a cubic equation, and finding your y-intercept and point of inflection, in fact. Now let us look at a case where they give you the graph and they now want you to find the equation of a cubic graph. Okay, so I'm going to state 3 conditions in which you can be presented a graph under, and how to use each to find the equation. The first condition, you can be given the x-intercepts. You can be given the x-intercepts of a cubic graph. Remember, a cubic graph has 3 x-intercepts. So you can be given the x-intercepts. Secondly, you can be given the turning points, or the local maximum, local minimum. And we know how many do we have for a cubic graph? We have 2. So you can be given the turning points. Or thirdly, they can give you the derivative, like they can give you the graph. How do I put it? They can give you the derivative graph, like your f prime x graph. They can give you the derivative graph or the derivative equation and ask you to draw your f at x, your cubic graph, from the derivative. Okay, I hope you are with me. So these are the 3 conditions, and let us take it now from your x-intercepts. If they give you x-intercepts, how do you find the equation of a cubic graph from x-intercepts? So let me draw just a typical cubic graph that goes like that, and our graph passes at that point, and also at that point. Okay, it's not a very nice cubic graph, guys. You know, I always struggle to draw this side, but it is a cubic graph, by the way. So our first x-intercept, it's -1 and 0, and then our 2 last x-intercepts is 2 and 0. You see, if it is turning there, it means it has 2 of the same x-intercept. We still say it has 3 x-intercept. The equation that goes with your x-intercepts would be y equals to a x minus x1, x minus x2, x minus x3. Because remember, when we were factorizing to find the x-intercepts, you ended up with 3 brackets which you equated to 0. And then our x values, we are going to put in your x-intercept. The first one would be x plus 1, and then the second one and the third one would be the same. So if you have a graph, most importantly, that has a turning point that is also an x-intercept, it means the graph has 2 x-intercepts that are the same here. I'm going to write it as x minus 2, x minus 2. I hope you're still with me, guys. Now I've written all of my x-intercept in this format, and there's something that I missed. So if they give you an x-intercept, I'm just going to add here and just one other point, or maybe one other coordinate. So we can see the graph crosses there, and the graph crossing there, let's say the y-intercept is 2 and 0. So now what is important is for us to find the value of a. In order to find the value of a, we're going to substitute the other point. We substitute the third coordinate that we have there is your 0 and 2. So it means to find a, we need to substitute 0 and 2. So we have 2, it's equals to a, 0 plus 1, 0 minus 2, 0 minus 2, which is a 1 times negative 2 times negative 2, it gives me 4. So that would be a times positive 4, meaning a is 1 over 2, so the value of a is a half. Now that we have found a, we have y, it's equals to 1 over 2 x plus 1. I'm going to FOIL that. That must give us x squared minus 4x plus 4, and then I still need to FOIL that and that. So I'm going to have x cubed minus 4x squared plus 4x minus x squared, no, plus x squared minus 4x. I hope you're still with me, guys. And that now leads us to 1 over 2 x cubed. So if I check there, we had said negative 4x squared. So the negative 4x squared plus 4 I'm just checking if I multiplied that correctly. So x cubed minus 4x squared plus 4x plus x squared, okay, I omitted the last term, plus 4x minus 4x squared plus 4, okay, and then negative 4x squared plus 1, it's negative 3x squared, plus 4 minus 4 is 0, and we're only left with plus 4. So it means y is 1 over 2x cubed minus 3 over 2x squared plus 2. There we have the equation. I hope you're still with me. And this is when you have your x-intercepts. And then the second condition is when you now have the turning points, or when you have your stationary points, or your local minimum and your local maximum. So what we know already about the turning point from when we were sketching, we had seen that every time when you want your x-intercept of your turning point, you need to derive the first derivative. You need to do f prime x, and then you equate it to 0, then you solve for x. But now what if they give you a graph that now has those turning points, but we need to use those turning points to find your what? We need to use the turning points to find the equation of the graph. Okay, so let us have a look. So we have one graph there that is f at x, and our f at x has a turning point over there of 0 and negative 2, and then the second turning point is over there and is 2 and 0. Okay, so we still use the same approach. We say whenever you are looking for a turning point, you derive, you solve for x on the derivative by equating the derivative to 0, then you find x. You take that x, you put it back to the original equation. So here they say they've given us the graph of f at x is negative x cubed plus bx squared plus cx plus d. So this is the graph that they have given us. So let us do what we normally do. First derivative is going to be negative 3x squared plus 2bx plus c, because c, d and b, these are numbers. So we treat them as we treat them as constants. So this is my first derivative, and I know I would equate the first derivative to 0. So 0 equals to negative 3x squared plus 2bx plus c. So I'm going to start by substituting the x coordinate there, because yes, if I was looking for an x coordinate, I would equate this to 0 and solve for the x there. But now I do have that x, is that 0 there. So I'm going to have 0 equals to negative 3, 0 squared plus 2b, 0 plus c, and all of that is going to give me 0. So our c would be equals to 0. So we have already gotten this part. Let us now find b. Still on the second derivative, the first derivative, I'm now going to substitute the second turning point. So the second turning point is 2, and the x value is 2. So this 0 is not that one, guys. This 0 is f prime x is equals to 0 at the turning point. Yes, at the turning point, the gradient is 0 because it's a straight line. So I have 0 equals to negative 3, 2 squared plus 2b times 2 plus 0, because our c was 0. So we have 0, it's equals to negative 12 plus 4b, which makes b to be 12 over 4, and that is 3. So now we have b, we have c. We can put them on the original f at x equation, negative x cubed plus bx squared, but our b is 3, so it's going to be plus 3x squared plus cx. Our c is 0, so we don't have, plus d. So now we need to find d. How do we now find d? Can we get d directly on the graph? Yes, no, yes we can, because remember when we started with this part, we had said d is your y-intercept, and already y-intercept is where the graph crosses this line, and we can see the graph crosses this line there. It means that turning point is also your y-intercept. So it means our d is the negative 2. So our equation is f at x equals to negative x cubed plus 3x squared minus 2. That is our equation. I hope you are still following, guys. It means whenever they give you a graph and they say find the equation, check what they have given you, especially with this part of doing first derivative, especially if they give you the turning point. It is very important that you do first derivative, okay? And then the third, which is the last condition, is when they give you the derivative graph. The derivative graph. So they say given f prime x. Remember we had said, before I can even get in there, we had said when you have the equation of a cubic graph, the moment you derive it, the first derivative is a what? It's a quadratic or a parabola. And then when you derive secondly for the second derivative, that should be your linear equation or a straight line graph. So it means if they do give you the derivative, that would mean they would have given you the equation of a parabola, or they would have given you the graph in terms of a parabola. So the question goes, given f at x, f prime x which is the derivative, so it's the derivative of f at x equals to ax cubed plus bx plus cx plus 8. So this is what they've given us. They want us to find that equation. They've given us the graph also. Sorry, we also have a graph. Remember, they've given us the graph of a parabola. So the graph goes something like this. And our coordinates on the graph, we have -2 and 0. We have a 4 there. We have 6 and 0. So because they want us now to find the original, we are still going to take that and derive it. So finding f prime x, it's going to be 3x squared plus, sorry guys, I omitted a 2 there, 3x squared plus 2bx plus c. That 8 goes away because it's a constant. So this is the equation of that graph. And if we now shift a little bit to functions, we know when you have a parabola and they've given you your x intercept, or your x-axis, your x-intercept, you say y is equals to x minus x1, x minus x2. This is from functions, grade 11, grade 12 functions, not including the cubic. You would do that approach, and then you do have your x1, so you have x plus 2. And remember, if you take it directly from the graph, when it gets in the bracket, it must change. If it's negative, it becomes a positive. X minus 6, and if we FOIL that, we have x squared minus 6x plus 2x minus 12, and that is a x squared, not plus but minus, sorry, minus 4x minus 12. That is your y. And then we do have a third point there, that is 0 and 4. This is the y-intercept of the parabola, so we can substitute it. So we have 4 equals to a 0 squared minus 4, 0 minus 12, and that is 4 equals to negative 12a. So when we divide both sides, a is gonna be 4 over negative 12, which is negative 1 over, not 1 but what is 4 over negative 12 again? 1/3. Yeah, it's negative 1 over 3. So now we have found the equation of that. We can now how do I put it? We can now take that a back. So y equals to negative 1 over 3 x squared minus 4x minus 12, which is gonna be negative 1 over 3x squared plus 4 over 3x plus 4. So this is the equation of what? Of my parabola graph. Okay. And then, because on the equation, we know the equation of a parabola, that represents your a, that represents your b, and that represents your c. If we bring that equation of your exponential, f at x equals to ax squared plus bx squared. Oh, okay, we don't really have to bring this one. In fact, if we bring the derivative now, we said f prime x equals to 3x squared. 3x squared plus 2bx plus 2, wait, did I have, it's not 3x squared, I made a mistake. Okay, from this now, if we bring the derivative of this original graph, this one, would say f prime x equals to, so if we derive your ax cubed, is going to be 3ax squared. So we have 3ax x squared. Okay. Okay, now after finding that, we need to bring the derivative of what? The derivative of this original equation that they've given us, the cubic graph. So if we derive that, it's gonna be 3ax squared. So we are saying f prime x is 3ax squared plus 2bx plus just c plus c. Yes, we now compare these two. We know that this part goes with that part goes with that part, and that part goes with that part, meaning we can go and say yes, c is 4 directly, but now 2b would be 4/3. I hope you're still with me. If 2b is 4/3, it means b would be 4/3 divided by 2. It will be 2/3, and then 3a equals to -1/3, because we are saying that represents a, so that is that part, and our a would be -1/3 divided by 3. It would be -1/9. So now that we have found a, b, and c, we can now go and say f prime x equals to -1/9 a cubed. We had plus b, which is gonna be plus 2/3 x squared, and then our c was plus 4x, then our d was given as 8. This would be plus 8. I hope you are still following, you're still with me, guys. This is how you're going to move from a parabola graph, which is f prime x, to a cubic graph. This is how you're going to achieve that.
And now that we have looked at how you can come up with the equation, or how you can find the equation of a cubic graph under those different conditions, the next thing, or the last part, is to add on the theory questions, the type of questions that they can always pop on your cubic graph questions. So they can pop a question on your f prime x. So we have seen that f prime x, and we had stated that it has to do with the turning point, and we had said f prime x is the gradient. So they can ask for the values of x. Let me also write that. Values of x for which f prime x is greater than 0, f prime x is less than 0, f prime, okay, just one prime, f prime x is equals to 0, and also they can go as further as f double prime x is equals to 0. F prime x being greater than 0 means whenever you draw the slope anywhere on the graph, we want where is the slope increasing. F prime x greater than 0, we mean where on the graph can you draw a slope and the slope increases. Why do I keep on writing decreases? The slope increases. And then f prime x less than 0, it means where can you draw the graph, a line on the cubic graph, and or a slope on the cubic graph, and that slope decreases. And then f prime x is equals to 0 is the values of x where we have the turning points. So we know f prime x is 0 at the turning points, and lastly f prime x, f double prime x, we are talking about the point of inflection. So let me just make an example. Say we have a graph, a cubic graph, that has a turning point at, for example, let's say -2 and 3, and another turning point there at 1 and -2, and we have the point. Okay, I'm not going to put in the point of inflection now. And this, they say find the values of x. Find the values of x for which f at x, f prime x is greater than 0. You will go to your graph and you're going to draw positive slopes. Positive slopes on the graphs, you can see they can only be allocated there. So when x is less than that turning point there, or when x is greater than that turning point there. So the answer would be when x is less than -3, or when x is greater than, no, that should be -2, or when x is greater than +1. And then f at x, f prime x less than 0, if we are to draw a negative slope there, that negative slope would only exist between the two turning points. So you'd say when x is less than -2 and x is greater than 1. So we are saying when x is between -2 and 1, that's where you have f prime x being less than 0. That's how you can interpret, or that's how you can answer questions of f prime x. Don't think too much about it. Just know that f prime x says where can I draw the slope on the graph, and that slope increases under that condition or decreases under that condition. I hope this video has made much sense to you guys. Please don't forget to subscribe. Don't forget to tune in for more videos. I'm going to post the last part, which is application of calculus, and with that part we are going to wrap up with calculus, because I want us to get into preparation of June examination. I want us to focus next week on paper 1 of your grade 12 and grade 11. So I'm going to make videos going through paper 1, and please make sure you are tuned in and subscribe.